This is Physics 2110, Lecture 9, and today we're going to talk about current and resistance. So electrical current is the rate of flow of charge through some region of space. And the SI unit of current is an ampere, and 1 ampere is 1 coulomb per second going through some region of space. The symbol we use for electric current is I. So let's talk about the average electric current. Let's assume that we've got a system here where I have charges moving perpendicular to some surface area A. If delta Q is the amount of charge that passes through this A in time delta T, the average current through here is delta Q over delta T, the amount of charge per unit time. If that rate at which charge flows varies with time, then the instantaneous current can be found as dq dt. Now the charges passing through the area could be either positive or negative, or perhaps even both. Conventionally, we assign the current to the same direction as the flow of positive charges. The direction of current is opposite the direction of the flow of electrons then. And we're going to refer to any moving charge as a charge carrier. Now, how fast do charges actually move? So let's look at some charged particles moving through a conductor that has a cross-sectional area A. And N is the number of charge carriers per unit volume. And then if we multiply that by the volume, which would be the cross-sectional area times the length that I'm looking at, that is the total number of charge carriers in this gray area. The total charge is the number of carriers times the charge per carrier. So delta Q is the charge density, charge per volume, times the volume, times the charge of each individual carrier. Then the drift speed, that's the speed that the carriers actually move, is how far they move over how long it takes them to move. Or rewriting, putting delta x here into what we have above, we can write delta Q is equal to NA times the drift velocity, delta T times the charge per carrier. And then the average current is going to be delta Q divided by delta T, which is going to be NQVA. Now that charge carrier motion in the conductor, the charges just don't move from one side over to the other. As the charges are moving through a metal, there's the nucleus of all the atoms and the shell of electrons around them that are bound to it. The free electrons then will move and then will hit one and then may bounce in some other direction and will kind of randomly just bounce in any direction. Over time, though, the electron will slowly drift from one side to the other in the direction opposite of the electric field. So in spite of all those collisions, the charge carriers slowly move along the conductor with what we're going to call the drift velocity. Changes in the electric field that drive the free electrons travel through the conductor at near the speed of light. This is why when we flip a switch, it's effectively instantaneous. The electrons don't have to travel from the switch to the bulb in order for the light to operate. There's already electrons throughout the entire wire, and there's already electrons in the filament. They respond to the electric field set up by the battery. The battery is not supplying the electrons to move the entire length. It's establishing an electric field which pushes electrons the entire length of the wire. So, what is a value for drift velocity that would be, say, in copper? Let's look at a problem. I have a 12-gauge copper wire in a building has a cross-sectional area of 3.31 times 10 to the minus 6 square meters. If it carries a current of 10 amps, what's the drift velocity of the electrons? We're going to assume a copper wire. Copper has one free electron per atom that's going to contribute to the current. And we know the density of copper is 8.95 grams per cubic centimeter. So, 1 free electron per atom, and then there's Avogadro's number of electrons in 1 mole of copper. So the molar weight of copper is 63.5 grams per mole. The density of copper is 8.95 grams per cubic centimeter. So the volume is 63.5 grams over that grams per centimeter. It gives us 1 mole of copper is 7.09 cubic centimeters. So the density of electrons in 1 mole of copper. So in 1 mole of copper, we know there's 6.022 times 10 to the 23rd electrons, divided by 7.09 cubic centimeters, but I need that to be electrons per cubic meter, so there's 10 to the 6 cubic centimeters in a cubic meter, and that gives us 8.49 times 10 to the 28 electrons in a cubic meter of copper that are free to move. So I can take that and plug that in to figure out what my drift velocity is. Taking our equation for current and drift velocity, we solve for drift velocity, which is the current over the density, number density of the electrons times the charge electron times the cross-sectional area. We plug in all of our values, and we get the drift velocity is 2.22 times 10 to the minus 4 meters per second, or 0.22 millimeters a second. So electrons are not actually moving very fast in the wire. They're bouncing around a lot, but the amount of time it takes for the electrons to move along the wire is relatively slow. In this case, 5 seconds to move 1 millimeter. Now this drift velocity is fairly typical of the order of magnitude of drift velocities in lots of other metals. Now, sometimes we don't want to just talk about current, but we want to talk about a current density. And we're going to define J as the current density of a conductor. And it's the current per unit area. So the current density, I over A, is NQ times the drift velocity. This expression is valid only if the current density is uniform and A is perpendicular to the direction of the current. Current density has the SI units of amps per square meter, and the current density is in the direction of the positive charge carriers. It's a vector quantity. A current density J and an electric field E are established in a conductor whenever a potential difference is maintained across the conductor. The current density J is equal to sigma E. Now this sigma is called the conductivity of the conductor. And I know we're using the same variable again, but this is not a surface charge density that we were talking about in previous chapters. It's a completely different concept. We're using the same variable, sigma, but as a different physical quantity. In this case, sigma talks about how easy it is to get electrons to move in a given electric field. Ohm's law states that for many materials, not all materials, but for many materials, the ratio of the current density to the electric field is a constant, sigma, that is independent of the electric field producing the current. Most metals obey Ohm's law. Mathematically, we say J is equal to sigma E. And materials that obey Ohm's law are said to be ohmic materials. Not all materials follow Ohm's law. If they don't, we call them non-ohmic. Ohm's law is not a fundamental law of nature like Newton's laws, or the gravitational law, or the laws of thermodynamics. Ohm's law is an empirical relationship valid for only certain materials. So in a conductor, when I apply a voltage across the ends of the conductors, that voltage is proportional to the current through the conductor. And that constant of proportionality is called the resistance of the conductor. The resistance is equal to the potential difference across it divided by the current through it. The SI units of resistance are ohms. 1 ohm is a volt per amp. And resistance in a circuit arises due to collisions between electrons carrying the current with the fixed atoms inside the conductor. The inverse of conductivity is the resistivity. Rho is equal to 1 over sigma. Rho is the resistivity, and it has units of ohm meters. And the resistance is related to resistivity. The resistance of, say, a piece of wire is the resistivity times the length of the wire over the cross-sectional area of the wire. Again, this resistivity, we use the variable rho. It is not a volume charge density like we were using before. Same variable, completely different concept. In this case, resistivity talks about how difficult it is to move electrons through a material. Now there's lots of different values of resistivity. Notice here, silver, copper, gold, aluminum, all these metals have resistivities in the 10 to the minus 8 range. Those are all good conductors. Of course, we get down here, sulfur, quartz, glass. Glass can be up to 10 to the 14th for resistivity. Very difficult to move. Notice that there's 22 orders of magnitude difference on how easy it is to move an electron through silver than it is for glass. Every ohmic material has a characteristic resistivity that depends on the properties of the material and on the temperature of the material. The resistance of the material depends on its geometry and its resistivity. An ideal conductor has 0 resistivity, and an ideal insulator would have infinite resistivity. So let's look at some values of resistance. Let's say I have a cylinder 10 centimeters long and a cross-sectional area of 2 times 10 to the minus 4 square meters. What is the resistance of the cylinder if it was made out of aluminum or made out of glass? Well, we said resistance is rho L over A. It's going to be rho times L is 0.1 meters divided by the area given, and we're going to get 500 times rho inverse meters. So, rho for aluminum, we look up on our table, was 2.82 times 10 to the minus 8 ohm meters. We plug that in, and we get that the resistance of this cylinder is 1.4 times 10 to the minus 5 ohms. If I look at it now for glass, the resistivity of glass is 3 times 10 to the 10th, and the resistance then, if I plug that in, is going to be 1.5 times 10 to the 13th ohms. That's 18 orders of magnitude difference in its resistance. Now, how do you make resistors? Most circuits that you'll ever see or design have elements called resistors in them. And they're really used to control the current level in different parts of the circuit. Resistors can be composite materials or it can be a wire-wound resistor. And this picture here is all full of resistors of different types. This big resistor along the back here is a power resistor. It has some fairly thick wire that's coiled up in a coil, and I allow air to go through to get rid of some of the heat. I've got these little resistors here that you might see in a circuit board, or today we even have surface mount ones that don't even have wires that come out of it. Here's another wire wound variable resistor. So I can look at the resistance between this point and this point, and as I change the length of the wire by having the slider go back and forth, I can change the resistance. And similar things are going on here in these different variable resistors. Now, resistors can sometimes have the value of the resistance printed on them, but a lot of times in small resistors we use bands, the colored bands, to denote the value. And the color coding here is black, brown, red, orange, yellow, green, blue, violet, gray, and white. And then there's also gold, silver, or no band on the end. And we do that. So if we look at maybe these resistors here in the circle and we blow them up a little bit, we notice that we have a red band on the one on the bottom, a black band, an orange band, and a gold band. So the red says the first number is 2. The black says the next number is 0. So 2, 0. Now the third band is a multiplier. And orange says 10 to the third, so we're going to get 10 to the third. And the gold tells me about how good of a resistor is, what kind of tolerance it has. So I'd write that 2, 0 times 10 to the third ohms, or plus or minus 5%, or it's somewhere then between 19,000 ohms and 21,000 ohms. Now, if I have an ohmic material, which most resistors are made out of an ohmic material, the resistance is constant over a wide range of voltages. And if I were to look at the relationship between the current through it and the potential difference across the resistor, notice that we have a constant slope, and the slope is 1 over the resistance. Non-ohmic materials are those whose resistance changes with voltage or current changes. And that current-voltage relationship then is nonlinear. A diode is an example of a non-ohmic device. A diode actually lets current flow in one direction, but will not let current flow in the other direction. Now, resistance and temperature are related, and over a limited temperature range, the resistivity of a conductor varies approximately linearly with the temperature according to this equation. The resistivity is resistivity at some known temperature, typically at 20 degrees Celsius, times 1 plus alpha delta T, where alpha is called the temperature coefficient of resistivity, and its units are 1 over degrees Celsius. Now, since resistance of a conductor with uniform cross-sectional area is proportional to the resistivity, we can find the effect of temperature on resistance using the same equation. R is equal to some resistance at a known temperature times 1 plus alpha delta T. Now, if I look at low temperature region of the resistance versus resistivity, it's not always proportional. For metals, it's proportional down to very low temperatures. But a nonlinear region always exists at very low temperatures. So the resistivity usually reaches some finite value as the temperature approaches absolute zero. And that finite value here depends on such things as the impurities in the metal. So maybe it's not solid gold. Maybe there's a few silver atoms or different atoms of different materials in it, so the electrons can't move freely. Or maybe the crystal structure is not exact. And so little imperfections in the wires cause there to be some residual resistance even at 0 degrees temperature. Now that residual resistivity, I said, near absolute zero is caused by collisions of electrons with impurities and imperfections in the metal. High temperature resistivity is characterized by collisions between electrons and metals. That's the linear range on the graph. Now, semiconductors are materials that exhibit a decrease in resistivity with an increase in temperature. So they have a negative alpha. There's an increase in the density of charge carriers at higher temperatures. The next class of materials I want to talk about is superconductors. Certain materials, when the temperature reaches a certain critical temperature, we'll call it Tc, the resistance does something strange. Whereas before we said for some materials the temperature comes down and then it comes over at low temperatures to a finite value. Other materials, mercury being one, at a certain temperature, and this for mercury is at 4.2 K, the resistance goes from some finite value down to exactly 0. The value of Tc is sensitive to things like the chemical composition, pressures, molecular structures. But if I have a superconductor that has 0 resistance, and I set up a current in its superconductor, that current will persist without any applied voltage, since resistance is equal to 0. And one of the important applications of superconductors is a superconducting magnet. I can get extremely high currents in a superconducting magnet and get magnetic fields that are 10 or more times greater than a normal magnet. We use these in things like MRI units or the NMR that the chemistry students use to determine different compositions of compounds. The picture on the right here shows something called the Meissner effect, where superconductors actually will repel magnetic fields. We'll talk about that a little bit more when we talk about magnetic fields, but this cube right here is a magnet, and as it gets close to this pellet that's superconducting, the magnet will float above it, since the magnetic fields won't go in the superconductors. So let's talk a little bit about power. Now let's look at this circuit here. We have a new circuit element. Between C and D, we have this jagged line here. It's meant to represent a wire-wound resistor, and that's the circuit element for a resistor. So, as a charge moves from A to B, the potential energy of the system increases by amount Q delta V. That should be a delta. The chemical energy in the battery then must decrease by the same amount. As a charge moves through the resistor from C to D, the system loses this electrical potential energy during collisions of electrons in the resistor with the atoms of the resistor. And that energy is transformed into internal energy or heat in the resistor. So it corresponds to increased vibrational motion of the atoms in the resistor. The resistor is normally in contact air, so its increased temperature results in a transfer of energy by heat into the air. It also emits thermal radiation. And after some time interval, the resistor is going to reach a constant temperature, where the input of energy from the battery is balanced by the output of energy from heat and radiation. The rate at which the system loses potential energy as charge passes through the resistor is equal to the rate at which the system gains internal energy in the resistor. And the power is the rate at which energy is delivered to the resistor. The power is given by the equation P is equal to I delta V, where by applying Ohm's law we can get P is equal to IV, or I squared R, or V squared over R. I, of course, is the current in amps, R is the resistance in ohms, V is the potential difference in volts, and power then is in watts. Now, real power lines have resistance, and so these high voltage power lines have a resistance associated with them, and it takes energy and it takes money then to move power across those lines. And since power is equal to IV, which we said was I squared times the resistance, given a certain resistance, if I have high voltage, I have lower current. And by minimizing that I squared, by having small currents and high voltages, I minimize the power loss in those power lines. So how do we deal with power in electrical circuits? Let's say I have an electrical heater. It's constructed by applying a potential difference of 120 volts to a nichrome wire that has a total resistance of 8 ohms. What's the current in the wire and the power rating of the heater? Well, V equals IR, so the current is V over R, which is 120 volts over 8 ohms, so we get 15 amps moving through the heater. And then the power is I squared R, so that's 15 squared times 8 ohms, or 1.8 times 10 to the 3rd watts, or 1.8 kilowatts. So to review what we talked about today, we started talking about current. What is current? The definition of current is I is equal to change in charge over the change in time. We talked about drift velocity, how an electron might go all over, but eventually it drifts from one side to the other, and that what some typical values of drift velocity is. We talked about Ohm's law, a relationship between current density and electric field, or between current and potential difference. We talked about what resistance is and what a resistor is, and finally we ended up talking about electrical power.